There is a threshold built into the natural world. A boundary defined not by law or permission, but by physics, by depth, by darkness, by pressure. By distance so vast it defeats every human instinct toward exploration. For most of history, that boundary held. Then the instruments arrived. Cameras that survive pressures that would crush steel. Telescopes that collect light from galaxies that existed before Earth did. Drilling equipment that reaches through kilometers of ice into lakes sealed since the Miocene. Microscopes that resolve individual proteins folding in real time. And suddenly, humans were seeing things the universe had kept private for billions of years. Not all of it was what anyone expected. Begin at the bottom of the ocean. Not the dramatic trenches, the Mariana, the Puerto Rico, but somewhere quieter. The abyssal plain. The flat, featureless seafloor that covers more of Earth's surface than all the continents combined, sitting in permanent darkness between 3 and 6 kilometers down. For a long time, scientists assumed it was largely barren. Too cold, too dark, too pressured, too far from any energy source for life to organize in any meaningful complexity. The remotely operated vehicles that began mapping it systematically in the late 20th century found something else entirely. The abyssal plain is alive, not sparsely, not marginally, but in ways that continue to surprise. Creatures that produce their own light in patterns too complex to be incidental. Organisms that move across the seafloor in formations that suggest coordination. Jellyfish-like animals of a delicacy so extreme that collecting them destroys them. They have only ever been observed intact in the water, through camera lenses, dissolving the moment they contact anything solid. In 2021, researchers operating a submersible off the coast of Western Australia filmed a Siphonophore, a colonial organism, technically a chain of cloned individuals functioning as a single animal estimated at 47 meters in length, the longest organism ever recorded. It had been living, hunting, and growing in the deep ocean, unseen, until a camera happened to find it. The deep ocean covers the majority of Earth's surface. Less than 20% of it has been mapped at high resolution. What the cameras find every time they descend somewhere new is not emptiness. It is not what the models predicted. It is life, organized in ways that nothing in the surface world prepared biologists to expect. Move from the ocean floor to something far smaller and in its own way, equally alien. The human body contains approximately 37 trillion cells. Each one runs a continuous biochemical operation of staggering complexity. Proteins folding, molecules being transported across membranes, DNA being read and copied and repaired, signals being sent and received in chemical language that took decades of molecular biology to begin translating. Until recently, most of this was inferred. You could sequence DNA. You could identify proteins. But watching the machinery work in real time, at the scale where it actually operates, was beyond the reach of any instrument. Cryo-electron microscopy changed that. In the last decade, its resolution has improved to the point where individual atoms within biological molecules are now visible. Researchers are watching ribosomes, the molecular machines that build every protein in every living cell, operate in real time. They are watching viruses inject their genetic material into cells. They are watching the precise mechanical choreography of enzymes that have been running continuously in living organisms for billions of years. What this has revealed, repeatedly, is machinery of a complexity and elegance that surprises even researchers who have spent careers studying it. The molecular motor that drives bacterial flagella, the rotating tail that propels bacteria through fluid, rotates at up to 100,000 revolutions per minute, changes direction in a fraction of a second, and is built from proteins that self-assemble into precise configurations without any external instruction. It was operating in bacteria 2 billion years before any eye existed to see it. Seeing it for the first time, actually seeing it, not inferring it, has been described by researchers in the field as genuinely disorienting. Not because it defies biology, but because the gap between knowing something exists and watching it work is larger than anyone expected. Come now to the edge of the observable universe, or as close to it as current instruments can reach. The James Webb Space Telescope collects infrared light wavelengths invisible to human eyes, stretched by the expansion of the universe from the original light of objects so distant that the light has been traveling since shortly after the Big Bang. When Webb processes that light into an image, it is showing us something no human sensory apparatus could ever directly perceive. In its deep field images long exposures of tiny patches of sky, Webb has revealed galaxies existing less than 400 million years after the Big Bang. In cosmological terms, that is almost the beginning. The universe was less than 3% of its current age. Stars had barely begun to form. And yet there were galaxies. Structured, massive, organized, more developed than any model predicted they should be at that age. The light in those images left its source before Earth existed. Before the solar system existed. Before the Milky Way had taken its current form. It traveled for over 13 billion years, passed through the universe's entire subsequent history, and landed on a mirror orbiting a planet that didn't exist when the journey began. There is no way to stand in front of a Webb deep field image and not feel the weight of that timeline. Not because it is frightening, but because the human brain was not built to process 13 billion years as a felt reality. Webb makes you try anyway. And the attempt does something to the ordinary sense of scale that doesn't fully reverse. If this kind of content, the things instruments have revealed that nothing prepared us to see, keeps you watching, there's more on this channel. Subscribing takes 1 second. Return to Earth now. To the interior of the planet, a place as inaccessible, in its own way, as the edge of the observable universe. The deepest hole ever drilled by humans is the Kola super-deep borehole in northwestern Russia, begun in 1970, reaching a final depth of 12,262 meters before being abandoned in 1992 when temperatures exceeded equipment tolerances, 12 kilometers down. It sounds significant until you consider that Earth's radius is over 6,300 kilometers. The Kola borehole penetrated less than 0.2% of the distance to the center. What it found in that 0.2% was already surprising. At depths where the rock should have been dry, compressed by enormous pressure, the drill encountered water. Highly mineralized, chemically unusual, but water, seeping through fractures in the rock from hydrogen and oxygen atoms, bound in minerals, and released by pressure. Microorganisms were found in rock samples from several kilometers down, living in solid rock, in darkness, at temperatures approaching 180 degrees Celsius. The interior of Earth is not a dead, sterile environment. The deep subsurface biosphere, the community of microorganisms living in rock, in hydrothermal fluids, in the pores and fractures of Earth's crust, has been estimated to contain a biomass comparable to all surface life combined. Most of it has never been sampled. Most of it is entirely unknown. What lives in the deep rock, how it survives, how long it has been there, what evolutionary paths it has taken in isolation. These questions are almost entirely open. The instruments to answer them don't fully exist yet. The access is nearly impossible. But the organisms are there, in the dark, in the heat, in the rock, doing whatever it is they do in conditions that should, by surface biology's rules, preclude them from existing at all. And with light itself. Specifically with light from an event so energetic that the physics describing it approaches the edge of what current theory can handle. Gamma-ray bursts are the most energetic explosions in the universe. When a massive star collapses into a black hole, or when two neutron stars merge, the energy released in a matter of seconds can outshine an entire galaxy. The gamma rays, the highest energy form of electromagnetic radiation, travel across billions of light years and arrive at Earth's atmosphere, where they are absorbed before reaching the surface. In 2022, a gamma-ray burst designated GRB2-21009A was detected by satellites and ground-based observatories simultaneously. It was immediately clear that something unusual had occurred. The burst's energy exceeded anything previously recorded by a significant margin. It has been called the BOAT, the brightest of all time. But what made it scientifically strange wasn't just its brightness. In the aftermath, ground-based telescopes detected photons, particles of light arriving from the burst's location, with energies exceeding 18 tera-electron-volts. That energy level is, according to existing models of how photons travel through intergalactic space, essentially impossible. Photons at that energy should interact with background light fields in the universe and lose energy long before traveling the 2.4 billion light-years between the burst source and Earth. They arrived anyway. The explanations currently being considered range from the mundane measurement error, modeling gaps, to the genuinely exotic, including the possibility that the photons traveled through a slightly different configuration of space-time than standard models assume. None of the exotic explanations are confirmed. The measurement error explanation hasn't been definitively ruled out either. What the boat left behind is a dataset that physicists are still working through. An event so energetic that it stressed the instruments designed to detect it, produced photons that theoretically shouldn't have arrived, and generated more published research papers in its first year than almost any astronomical event in recent memory. The universe, at its most violent, produced something that human instruments were just barely capable of detecting, and that human theory is still working to explain. It happened 2.4 billion years ago. The light took that long to reach us. And when it did, it arrived carrying questions that nobody had thought to prepare for. The deep ocean floor, the interior of a living cell, the edge of the observable universe, the rock kilometers beneath Earth's surface, the aftermath of the brightest explosion ever recorded. None of these were accessible to human perception a century ago. Some were accessible only within the last decade. Each time an instrument reached somewhere new, somewhere the physics of human biology could never go, what it found required the existing models to expand. Not break, expand. That expansion is ongoing. The instruments are improving faster than the theories that interpret their findings, which means the gap between what we can see and what we can explain is, in some fields, currently growing rather than shrinking. That's not a crisis. It's a condition. The most productive condition science knows more data than framework, more observation than theory, more universe than map. There are things out there in the deep ocean, in the cell, in the rock, in the sky, that no human was ever evolutionarily equipped to perceive. The instruments changed that. And what they keep showing us, every time the resolution improves, or the depth increases, or the exposure lengthens, is that the universe was doing extraordinary things long before anyone was watching. It still is.